Hi, I'm Junjie Park and I'll introduce this paper about large-scale object detection. As you know, the open images dataset is one of the largest object detection dataset. However, these sort of huge datasets suffer from label-related problems because of its semi-automatic collecting and labeling pipeline. In this paper, the authors pointed the problems that can be caused when using large-scale dataset and provided simple but effective solutions. The first problem the authors mentioned is the objects explicitly and implicitly have multiple labels. The second one is the label distribution is imbalanced. So I summarize the types of the problems and the solution introduced in this paper. First, I will talk about the problems and then I will introduce the solutions. First, the explicit multiple labels refer the case that some objects hold multiple labels, including leaf and parent labels. As in the figure, the fruit is parent label and apple is the leaf label, but both labels are annotated on the same object. On the other hand, there's also the implicit multiple label problem caused by the limited and inconsistent knowledge of human annotators. The left graph shows the confusion pairs, and you can see that the flashlight is also annotated as a torch by mistake. As images of open images dataset are collected from open source in the wild, the label distribution is extremely imbalanced that both very frequent and infrequent classes are included. There could be some problems that frequent categories could be not trained sufficiently and there would be oversampling problem for infrequent categories. So in this paper, the author suggested two solutions for each problem. The first one is the concurrent softmax for explicit and implicit multiple label problems, and the second one is soft balance sampling with a hybrid training scheduler for solving the imbalance label distribution problem. First, the concurrent softmax is designed based on the softmax loss, but conventional object detection training scheme would restrain each other. So let's look into what is added to solve the problem. The first term is designed for solving the problem related to explicit multiple label problem. The 1 minus yj term can remove the suppression effects between explicitly coexisting categories in concurrent softmax. The second term is designed for solving the implicit multiple labels problem. The Rij denotes the concurrent rate of class I to class J. So this term can weaken the suppression effects between confusion pairs. For the soft balance sampling, conventionally images are sampled in sequence without replacement for training in each epoch. So in this case, originally, sampling probability is Ni over N, but this may degrade the recognition capability of model for infrequent classes. Because of this problem, the class-aware sampling probability PA was suggested as 1 over C, but this also may cause overfitting on infrequent categories and insufficient training on frequent categories. So from the two equation, we can rewrite the PA like this, and the alpha can be a balance factor here. So the authors suggest the balance factor with a new hyperparameter lambda. The lambda is 0 in the case of the non-balance sampling and will be 1 for the case of the class-aware balance. So this is a result of the normalized probability. However, even with the sub-balance method, there are still many samples of the frequent categories that are not samples. So the authors introduced the concept of hybrid training scheduler. First, training detector using the conventional method, and then fine-tuning the model with soft-balance strategy. So they conduct experiments on Open Images Challenge 2019 dataset. They explore the influence of concurrent softmax in training and testing stage respectively. They compared the different loss functions, and the concurrent softmax loss showed higher performance in the both cases of training and testing, as you see. Also, they compared different sampling methods, and soft balance sampling showed also higher performance. Interestingly, when the lambda is 0.7, the model shows the highest performance. Because if the lambda is 1, that model can solve the data insufficiency of infrequent categories, but it undersamples the frequent categories and causes the performance dropping on the former half categories. So I finished my presentation, and thank you for listening.